Welcome to session 2 in the series Analog Circuit Design using ADS, and in this series in this session I'm going to cover something with semiconductors and their devices, right? So let's put in here a title called semiconductors. Now we know that these semiconductors are either elemental form of semiconductors, elemental, right? They are elemental form of semiconductors. For example, you have silicon, you have got germanium, you have got right, carbon is not used, right? So elemental is silicon and germanium, and then you have got compound semiconductors, right? And examples are, so you can say this silicon germanium is also not a compound, actually it's still elemental. And then in compound you have got gallium arsenide, gallium nitride, right? So this is what we are going to talk about, right? So now we start with the elemental semiconductors. Now up till now we have seen that there is a covalent bond between silicon with other atoms, right? Silicon with other atoms, right? Now this is just a representation. In actual, what's going to have happen is this is going to be a face-centered cubic structure. And this is if there are all the elements are. So what is a face-centric cubic structure? So this is a lattice, right? So this lattice, okay, is has a lattice constant of 5.43 degree angstrom, and then there is 1/8 element here, and then there is one more 1/8 element over one-eighth atom over here, right? 1/8 atom over here, 1/8 over here. So in all, if I cover all the 8 corners, right, if I cover all the 8 corners, I am going to have, okay, so in all 8 corners I am going to have one atom, right? Now if I consider on the faces, there are going to be, on the faces, if they are going to be atoms, right? So there's going to be half over here, half on this one, half on this one, half here, half here, half here. So basically they're going to be 1, 2, 3. So I would have plus 3 here. So these are going to be face centered. Now what else is going to be there? They are going to be 2 on the diagonals. So if I take a solid diagonal in this lattice, one diagonal is this way, other diagonal is that way, so there's going to be like that. So how does it go? Okay, so there will be 4 actually. So there will be 2 on each diagonal, right? So there are going to be 2 on each diagonal. That means that they are going to be 4, 2 on each diagonal. So in all there are going to be 8 atoms in a cell, right? And this is known as a diamond structure, right? Now in this case, if I have a gallium arsenide, right, then we are going to have, arsenic is a bigger atom, gallium is a smaller atom, so we are going to have these 8 again, okay, 4 of gallium and 4 of arsenic, right? So this is again going to be adjusted this way only, but it's just that these 4 are going to be, let's say, arsenic, and then the 4 on the diagonal are going to be gallium, right? So 4 on the diagonal are going to be gallium, and then 1 on the all the vertices and 3 on the surfaces, so that will make 4 of arsenic, right? So I have written it reverse, so let me just correct this. Okay, so gallium is going to be smaller than arsenic, so arsenic will be on the surfaces and the edges, so that is going to be 1 plus 3 formula, and here it is going to be 2 plus 2, so there will be 8 of them. So this is known as zinc blend structure. So this is how the gallium arsenide is going to be. Now we know that as long as electron is part of it, part of a covalent bond, the energy associated with it, okay, that is known as valence band. And this valence band has got many sub bands, and that is NV. Okay, so this is called valence band. Okay, and then there is going to be a conduction band, which again there are going to be number of sub bands in here, that is NC. Okay, so this will be called conduction band. So okay, so the energy which is possessed by these electrons which are part of covalent bond, that is called a valence band. While the minimum energy which is or the energy which is required to have the electron free from being captured by any of the nucleus, that is called conduction band, right? And the difference between them is 1.1 electron volts in case of silicon. This is called as band gap. Okay, so now if I was to say an electron is bumped by supplying certain energy from the bond, so this electron basically transitions from valence band to a conduction band. So when the electron leaves, it leaves behind a positively charged hole, and when it reaches a conduction band, you have an electron. So basically hole is nothing but the absence of an electron in covalent bond, and electron in conduction band is a free electron which is not possessed by any of the nuclei, right? So this is the story here. So we know that electron and holes are generated in pairs. So this can be done by raising the temperature most easily, or it can be done by stress, or it can be done by a photon, right? So anyways I can supply energy. Most prominent is temperature. So now these electron holes pairs which are generated because of temperature, they are known as intrinsic carriers. Intrinsic carriers. Okay, so they are represented by Ni per meter cube. I'm going to always keep the metric system as MKS. So that will be equal to root of NC and V e raised to minus Eg in joules divided by twice of kT, where K is Boltzmann constant, right? And T is the temperature in Kelvin. So Eg is the energy band gap. Now if you consider this energy band gap in electron volts, so I will put a E here subscript, and then I have to multiply by Q. So this is going to be the intrinsic carrier density at any temperature. So now let's say the temperature is 0, then this quantity becomes infinity. So Ni at T equal to 0 will be equal to so this is e raised to minus infinity, that is 0. 0 multiplied by root of NC and V is 0. So at absolute 0, okay, so T is equal to minus 273.16 degrees Celsius or 0 Kelvin. Okay, so as 0 Kelvin, this is going to be 0. So now you see that intrinsic carriers, okay, so one thing to observe here are intrinsic carriers. Intrinsic carriers are a strong function of T, are strong function of T. Now this is a problem, right? Now the problem goes like this. If you want to make a certain circuit using intrinsic carrier or intrinsic semiconductor only, right, the purest form of semiconductor which has only electron hole pairs which are a function of temperature, then if you design the circuit for one geographic location where temperature is like 25 degrees, and then take it to another geographic location where the temperature is minus 40 degrees, then the temperature dependency is so high, then the circuits are not going to behave properly, right? Now let's look at what is the order of this. The order of this is basically 10 raised to 16 per centimeter cube, or rather I would say, so 2 raised to minus, so 10 raised to 16 divided by okay, 10 raised to minus 2 centimeter cube, right? So this will become 6, right? So 10 raised to this, 10 raised to this, and 10 raised to this. So this will be now meter cube. So this will be equivalent to 10 raised to 22, 22 per meter cube. So Ni is of the order of 10 raised to 22 per meter cube. Now this brings in a very strong dependence on temperature. That's why to reduce temperature dependency we introduce what is called a dopant. So the dopant is going to, so now the analogy goes like this. If I have a line, without cutting and erasing this line, I have to make this smaller. How would I make this smaller? One way is I'll make a bigger line. So now this line looks smaller, right? So for example, let's say there were let's say 10 electron hole pairs which were intrinsic, right? And somehow I introduced holes or electrons which are going to be 100 times of that, so let's say 1000. So now if these 10 exist or though don't exist, so basically if temperature is high or low, it doesn't matter, this is going to affect only this 10. This 1000 is not going to be affected. So the number you are looking at is the number of electrons are going to be between 1000 to 1010. So the dependency of temperature has gone down, right? So this is how we bring down the dependency. Now what are these dopants? So if there is silicon in the outermost orbital has got 4, which it shares with the neighboring 4 silicon atoms, right? Rather you can think it in terms of diamond structure, right? Now what will happen is if I replace one of these, okay, so if I replace one of this with arsenic, okay, so now arsenic is bonded within silicon and arsenic has 5 electrons, so 4 have bonded, 1 is free. Okay, so 1 additional is there, so per arsenic atom. So if I had a dopant of arsenic, okay, so arsenic is called pentavalent, pentavalent element, while silicon is quadvalent, right? So you have a pentavalent here, so you have one electron extra per arsenic added. So let's say the doping density is Nd per meter cube, right? So now the number of electrons are going to be approximately, so the number of electrons, so that I represent by n, and the type of material here is going to be n. So this is approximately, because what is the approximation here? This factor of 10, right? So roughly it's going to be Nd, right? So this is referred to as doping, right? So now if Ni is of the order of 10 raised to 22 per meter cube, then you should go with a doping which should be at least doping should be greater than 10 raised to 25 per meter cube, right? So it should be 1000 times at least. So that's what it is. So what is the minimum value of doping? I should be at least 1000 times of what intrinsic is, so that the temperature dependence is gone. So this type of material where there are excess electrons which are independent of temperature, okay, these are known as extrinsic semiconductors. These are known as n-type semiconductors. So this is going to be what you call a n-type semiconductor. Now same thing you can do with boron, right? So if you have silicon, then you have boron, then you have silicon, then there is one missing, so I put a dotted line, silicon, and that's how the bonding is, right? Now one is missing here, okay, so that is equivalent to a hole because it's in the valence band, right? So this is an additional hole which you have introduced. So you have introduced one hole per boron atom. So if you dope with Na per meter cube, right? So this would be called P in a p-type material, which will be approximately equal to this. So the analogy goes again, it is much higher than the intrinsically generated holes. So you can ignore those intrinsically generated holes. So then the total number of holes will be approximately equal to the dopant, which is independent of temperature. So in this type of material would be called a p-type material. Now something interesting happens in terms of energy band. Okay, now I'm going to do an energy band of p-type and n-type. So let's say n-type first. So I'm going to have more, so let's say intrinsic, right? So if you have intrinsic silicon, then what's going to happen is electron holes are generated in pairs. Okay, so this is valence band, that's conduction band. So electron holes are generated in pair. So if I look at the average energy would be somewhere in the center. That is known as Fermi level, right? Now the average energy is in the center of the band gap, right? So this is going to be intrinsic semiconductor. Now in case of, let's say, p-type, what's going to happen? In p-type you have less number of electrons, so the average energy basically has gone down, or so basically the Fermi level would have moved down like this. So let's say this is Fermi level here. Now this is going to be in case of a p-type material, and this is in case of an intrinsic. Okay, now let's look at n-type material. In n-type material there are more electrons here. You have put in arsenic, which has excess of 1 electron per atom, right? So the same energy diagram, but this center of gravity in terms of energy has gone up. So the Fermi level has gone up. So this is the Fermi level in intrinsic, extrinsic, intrinsic, p-type and n-type. Now on their own, okay, these different materials, so everything is silicon here, right? So it's just that one is pure silicon, other is silicon plus boron, a trivalent impurity, and this one is silicon plus arsenic, right? So this is n-type, p-type. So that's the whole goal of doping, is to dope it to a level which is much higher than Ni, so that the temperature dependence is gone, right? And so we have two types of material, which are p-type and n-type. Now if I was to put these together, okay, so if I was to take one section which was a p-type, and to this I add another section which was n-type, okay, and then I have a distinction in between here like this. Okay, so this side is basically, let's say, p-type, and this side is n-type. Okay, so I have come through only one equation here, so which you should remember. So this equation is equation number 1. This is with the relationship between intrinsic carriers as a function of temperature and Nc and V. Okay, now if you want to understand the dependence, it goes like this. If for example there are Nc and Nv states to be occupied, then the intrinsic carrier density has to depend on the empty states, right? So that's why there is a root of Nc and V here. Then if Eg is large, then Ni is going to be small, because less electrons can cross over, right? So if Eg is large, then Ni is small. And similarly, if temperature is low, then Ni is small, right? So the dependence is very clear, right, with this equation, with the intrinsic carriers. Now let us look at this. Now here I'm going to write here, this is a p-type. So if I look at holes with a representation using p and then a subscript p for p-type, this is approximately equal to Na per meter cube. And here N, so these are called majority carriers, is equal to Nd per meter cube, right? Now there is something called law of action of mass. Okay, so these are some things which you should well, you should just believe me in. If you want, you can read about this if you want to prove to yourself. Okay, Ni square will be equal to in any material will be number of electrons. So basically Ni is geometric mean of number of electrons and number of holes. Right. So if I consider a p-type material where I can represent number of electrons, or sorry, number of holes as Nd, then you have Nd into number of electrons. So number of electrons is N with a subscript p, right, would be approximately equal to Ni square. So now Np in a p-type material, right, Np is approximately equal to Ni square over Nd, and Pp we know is Na. What did I do? Ni square over Na. I'm doing mistake here. Okay, let's write this again. So number of holes is basically Na. So then Np is equal to Ni square over Na. Okay, so that's correct. So this is p-type material. You have majority carriers Pp, minority carriers Np. Np is approximately Ni square over Na. Now if you consider the n-type material, what do you have? You have Ni square is approximately equal to Pn into Nd. So Pn is approximately equal to Ni square over Nd. Okay, so now we are clear on what are the majority carriers. Majority carriers on p side are holes which are Na per meter cube. My majority carriers on n-type side are going to be electrons which are going to be Nd per meter cube. Then minority carrier on p side are going to be electrons Np, which is approximately Ni square over Na, and minority carriers on n side are going to be holes which are approximately equal to Ni square over Nd. Now when we put these two together, something interesting is going to happen. Okay, so let me just draw these diagrams which are going to be very helpful later on. Okay, so I'm going to write here these equations. Okay, so let's consider that this one, okay, is where there is a epitaxial junction, right, and then there are two sides to it, right? Okay, so there are two sides to this. Bear with me for this slow stuff. Okay, so there are two sides to this. One side is p-type, other side is n-type. So let's represent this is a p-type here, and then there is going to be n-type over here, right? And this is the epitaxial junction, right? And sorry, so that's the epitaxial junction. Now I can take the liberty of joining these like this because I cannot make it very straight. Okay, so this side is going to be p-type and this side is going to be n-type, right? So here we are going to have Na and Nd. Here you're going to have Ni square over Na and Ni square over Nd. Okay, now what's going to happen is the following. When you put it there, these two together, something is going to happen. Okay, so let's draw the band diagram over here. Okay, so this side you have got the how's that, how did it move? Sorry about this, I'm new to this software. Okay, so this side, let's assume up to here. That's so strange. Okay, this is your band, let's say conduction band, and over here I'm going to do a valence band. Okay, now what is going to happen is when you put them together, okay, the energies on both sides have to balance. That means that their Fermi levels will come together. So in P side the Fermi level is lower, and on the N side the Fermi level is higher. So let's go this way. So this is, let's say, is Fermi level, right? Now what's going to happen on the N side? Because now it has moved down. Now how does it move down? Okay, there is only one way of moving down, is to lose energy, right? So to move down in energy you must have lost some energy, right? So let me just clear this. So that's an exaggeration, but let me just put it there. This scaling I don't like. Okay, so like this, and then on this side you will have the same gap. Okay, so you're going to have this one and this one. Okay, so now what has happened? What has happened is, if you want this Fermi level to line up, now in n-type side, if you remember, okay, so I don't want this. So in n-type side, if you remember, the Fermi level is way up, and the p-type side the Fermi level is way down. Now this has to become equal. The only way it can become equal is if these electrons move to that side. So the electrons are going to move from n-type side to p-type side to balance the energy, right? Then the energy on this side will go up, so the entire band structure will move up. On this side the entire band structure will move down, right? And then you have this. Okay, so it's ugly, but it's okay. So what has happened over here is electrons have moved based on energy so as to balance the energy. This is known as diffusion current. Diffusion, D-I-F-F-U-S-I-O-N, current. Okay, so you understand diffusion current is due to energy imbalance, why they are moving. It is unlike the drift current. Drift current is because of the field. Okay, so you should understand the difference between the two. Okay, drift current is because there is a field applied, and under the influence of the electric field the carriers are going to move, so that is called drift current. Now diffusion current, unlike drift current, is based on the energy level. So for example, let's say there are two branches in one is electronics and other one is what you call mechanical. And mechanical people are usually energetic because they do everything with their hand. In electronics they are kind of low energy. Now when you put them together in something like a program, okay, a get together program, they mix with each other, and then the overall group has the same energy level. Why? Because more energetic mechanical guys, they mixed with the less energetic electronic guys, and the overall group has the same energy. That's the Fermi level. So that's what has happened. So this movement based on energy, okay, is called diffusion current. Now once you do this, what's going to happen is on this side there are Na per meter cube electrons. uh, Sorry, on this side there are Na per meter cube holes, and there are Nd per meter cube electrons on this side. Okay, so when these electrons move on that side from N side to the P side and the Fermi level balances, what's going to happen is the following. Like for example, let's say there is a bus stop, and in bus stop there is a bus starts from a certain bus stop, right? And the bus comes in empty, and then suddenly people rush in to occupy the seats, okay, because those are empty seats. So similarly, these are the persons which move from N side to the P side. So what are they going to do? They are going to occupy the empty seat, and the empty seats are Na, right? Na per meter cube. So all the electrons are going to be occupying the free holes, or basically there is going to be a recombination, right? So what is going to happen is the left hand side of the junction will become negatively charged. I'll show you how. So let me just draw. These lines are going to be helpful later on. Okay, so up to this, let's say I'm going to draw a dotted line. And on this side, let's extend this line. Kind of strange, kind of difficult to place. Okay, so let's just extend this. Okay, and then this side I have gone way this way. Then I'll explain you what is happening over here. Okay, now I don't want a scale ruler. Okay, maybe yes. Let's just shift this angle. Okay, so now I'm going to look at this junction in terms of charge. So on this axis, I'm going to talk about charge. So I would say charge, I would say CH, charge. Okay, so this is the distance, sorry. Okay, this is the distance, and that's the charge. So this is the distance. So this axis is going to be distance, and this axis is going to be charge, CH. Okay, so what I was saying is when electrons cross from this side to that side, okay, as soon as they cross the epitaxial junction, right, they are going to occupy all the vacant positions, which is Na. So the density is going to be Na per meter cube, and the total charge density is going to be here as minus QNA, and this will happen, okay, up to a certain distance, which is called depletion depth. So this is called depletion region, minus W1. And then on the other side, W2, what's going to happen is, you can think electrons are doing in conduction band, but they are also doing this in valence band, right? So electrons are moving from this side to that side, which is equivalent to holes moving this side. So now when holes move in this side, they have Nd electron as vacant states. So all the holes which move in occupy Nd vacant states or holes. So then this, so let me just make this, okay, so that you can understand it. Okay, so over here this is going to be this, over here it's going to be this. So this density is going to be Q and D per meter cube, and the total charge is going to be balanced. So how the total charge will be? So total charge on the left hand side is this area, total charge on the right hand side is this area. So this side is negatively charged and this side is positively charged, right? So now if this side is positively charged, the total charge is Q and D W2, and here it is going to be minus Q and A into minus W1. So that is going to be Q and A W1. Okay, now these charges have to balance because you know it is electrically neutral, right? The junction is electrically neutral, so you have a relation NaW1 is equal to NdW2. Now, so that relation comes in. So up till now I have seen this relation, right? So up till now I have seen one relation which was due to intrinsic, then there was another relation due to law of action of mass, okay, so which is basically here and here. Then the other one is going to be here, relationship here, which is the charge balance, right? So the charge is distributed like this. Okay, so now if the charge is distributed like this, then I can say, okay, so then I'm going to introduce you to another equation, that is dou 2v dou 2 dou okay dou 2v by dou x square. So this distance I am considering as x, okay, so that you don't get confused. Dou 2v by dou x square is equal to minus rho v over epsilon. This is called Poisson's relation. Okay, Poisson. Okay, so this is called Poisson's relation. Now I can take this equation for the left hand side. So the equation for the left hand side would be dou 2v by dou x square would be equal to, rho v is minus q n a, so minus minus will cancel, q n a over epsilon, right? So that's the relation. On the right hand side, what do you have? You have dou 2v by dou x square is equal to minus q n d over epsilon, right? So that's the relationship. Now let's integrate this. Dou 2v by dou v by dou x will be equal to q n a over epsilon plus, so if you integrate this with respect to x, there will be x here. Okay, so if you integrate with respect to x, there is x here plus constant c. Okay, q n a over epsilon x plus c. Now the electric field E is minus dou v by dou x, so I can say E left will be equal to, so basically this is nothing but area under this curve. So if I was to draw another, so now I'm going to talk in terms of field. So earlier I have talked in terms of charge, so that is a diode in terms of charge. Now let's see in diode in terms of field what's going to happen. Okay, so let me just extend these lines, draw some more, and this side. And let me extend this line. Come on. Okay. I will look for a shortcut so that you don't get bored. Okay, so I am going to integrate the charge with respect to this x, and that will be the area under this curve. So the area under the curve is going to be like this. Similarly, area under this curve should be like this, right? Sorry. this is minus W1, this is 0, and this is W2. Okay, so now E left is going to be equal to minus QNA over epsilon x, and this is a proportionality constant, so I need not bother about the sign. Okay, now the limiting condition is this field exists only when there is a charge. So if you go beyond on the left and right, there are no charges, so there is no question of a field, right? So the field exists only in this region, which is called depletion region, right? So the boundary conditions are E left at minus W1 equal to 0. So if I substitute this, then C will become equal to minus QNA over epsilon W1. And if I substitute it back, E left would be equal to Q minus QNA over epsilon x plus W1. Right, so now let's substitute. If x is equal to minus W1, then E left equal to 0, and x equal to 0, then E max would be equal to, from the left hand side it will be equal to minus Q NA over epsilon. Let's make it clear. Minus Q NA over epsilon x plus W1. So x is 0, so it will be W1. So it will be W1. Correct? Now let's look at the right hand side. Right hand side would be E right is equal to QND over epsilon plus C, and equal to 0 at W2. So then at x equal to W2, the field is going to be 0, then C is equal to minus QND over epsilon W2. Now substitute this, you have E right is equal to QND over epsilon x minus W2. What has happened? Let me put it on a pause function. Okay, so I'm going to continue. I don't know what happened at this point in time. Maybe something got disconnected. I don't see a reason for something to disconnect. Okay, so okay, fine. So E left, E right. Now this is first integral. Now at the center they are going to be equal, which is going to be, again, if I put x equal to 0, this will be minus Q ND W2 over epsilon. Correct? I'm so scared of this because this is a new software, and last time, you remember in the previous session, the voice was gone. Okay, anyways, so what's going to happen is this equation holds good because at the center x equal to 0, these two quantities are equal because NaW1 equal to NdW2, so that's fine. Now let us look at what happened to one more level of integration. Okay, so I'm going to put it here itself. So I'm looking at one more level of integration here. This is x. Okay, so now on the left hand side you have got q, so dou 2v by, sorry, not dou 2v. Okay, what you have is dou v by dou x equal to minus E left, which is equal to QNA over epsilon x plus W1. Now if I integrate this once more, I will have QNA over epsilon x square by 2 plus W1x plus C. Now if I assume that the initial value condition is that the left hand side, which is p type, is basically grounded. So if I assume this, then the voltage to start with will be 0. So in that case the C can be evaluated as at minus W1. Okay, at minus W1 the C value will be minus W1 will be W1 square minus W1, so it is going to be Q NA over epsilon minus W1 square, right, by 2, that's C. So substituting V left would be equal to q n a over epsilon x square by 2 plus w1 x plus w1 square by 2. So v left is that. So it's going to start with 0 and it's going to become that's this stupid. So I understood what that is. Don't worry. Okay. So this is the left hand side. Now at x equal to 0, I would have v1. So this value is v1. Okay, so v1 will be, if I substitute x equal to 0, then I have q n a w1 square by twice of epsilon. So that's going to be v1. Now on the other side, okay, I have to do the same thing with this as the initial condition. So what I have here is v right. E right will be equal to dou v by dou x would be minus of E right, which is q n d over epsilon x square by 2 minus w2x plus c. Correct? So I put a c inside, which is wrong here. So let me make a correction here also. The c was outside so that people don't get confused. This is proportionality constant, right? So similarly, I want to find out at x equal to 0, right, what is going to happen, right? So let's integrate this. So we have v is equal to minus q n d. So I have already integrated this, sorry. So this will be equal to v. Okay, so v equal to v1, right? So v equal to v1 at x equal to 0. So v is equal to v1 at x equal to 0. So v is equal to v right side is going to be equal to minus q n d over epsilon x square by 2 minus w2x plus v1, right? And v1 is q n a, right? So this will be minus q n d over epsilon x square by 2 minus w2x plus q n a w1 square by twice of epsilon. Now I can take q and epsilon common, and then I can also take a nd common. Then what do I have? X square by 2 minus w2x, and this term would become minus, and I would have na divided by na. So na square w1 square, so that will be nd square w2 square. So you will be left with nd w2 square by twice of na. Okay, so this is going to be v right, and it will go like this, and then it will be flat. So this is voltage. So I have seen a p-n junction diode in terms of charge. I have seen p-n junction diode in terms of the energy band. I have seen field across the p-n junction, and I have seen the potential which is developed. This is called the built-in potential, or phi naught, which will be equal to, so if I substitute in this equation, w2, x equal to w2, then what do I have? v1 plus v2. Okay, that will be q n a w1 square by 2 plus twice of epsilon plus q n d w2 square by twice of epsilon. So that is going to be equal to phi 0. Now if I apply external potential, then it will be VR, right? So now this basically, okay, now this is one equation. So let's say this is equation number 5. So this is equation 5. Okay, so now what's going to happen is I have another equation, which is equation number 3. So using 3 and 5, I can find out W1, which is the depletion depth. Okay, so that W1 will be equal to, you can substitute here, right? Okay, twice of epsilon xi 0 plus Vr divided by Qna, okay, into, okay, so this is going to be square root of, right, raised to half. Okay, so will be Qna. Okay, Qna will be common here, right? So let me just write this equation: twice of epsilon xi 0 by plus Vr divided by Qna into, I will figure out I'll figure out a way for this one, so bear with me. Okay, so this one will be, okay, and W2 by symmetry is going to be twice of epsilon xi 0 plus Vr over Qnd Na divided by Na plus Nd. Let's put them in bracket. Okay, so raised to half. So let's look at the charge. So the charge, the magnitude of charge on the left hand side will be Qna times of W1. So that would be equal to twice of epsilon xi 0 plus Vr times of Qna square. So Qna Nd divided by Na plus Nd raised to half. And the charge on the right hand side will be equal to twice of epsilon xi 0 plus Vr. Multiply this with Qnd, you will have again Qnd Na by Na plus Nd. So you see that the charge on the left hand side is same as the charge on the right hand side. These two charges are the same. So the diode is electrically neutral. Okay, so what I have shown you over here is various equations. So for a diode, p-n junction diode. So this is what I have discussed here. Now p-n junction diode, okay, there are some more characteristics to a p-n junction diode, and these are, let's say if Na is going to be much larger than Nd. So what it means is that W1 is going to be much smaller. What has happened here? So W1 is going to be much smaller than W2 to an extent that W1 vanishes. So this becomes a one-sided. So if Na is much larger than Nd, then W1 is much smaller than W2. So the depletion region exists only on the one side, which is going to be the least dupe side, which is in this case is going to be Nd, which is going to be n-type, right? So these are called single-sided junctions, right? So in that case W1 will be approximately 0 because Na is much larger, so this term will become, so this term, okay, is much larger than Nd, so this term will become 0 and W1 will become 0. Now in this case then because Na is much larger, then this term will become 1. So the total depth will become twice of epsilon xi 0 plus Vr over Qnd raised to half. Okay, so this is a one-sided junction. So I'm going to stop here. I started with the semiconductor devices, right? And I explained you p-type, n-type, intrinsic, and then I basically told you what happens when you put p and n together. And when you put p and n together, this is what has happened. Now one more characteristics which I need to discuss is this. Here I'm not going to draw, I'm directly going to use freehand. So this is epitaxial junction. Let's say this is W1 minus W1, and then this side is W2, right? Now if you see in terms of carriers, Okay, so the carriers are going to be becoming 0 here, right? And over here, so this is n side, so this is nn, which is approximately equal to ni square over nd, right? And this is approximately ni, right? And this gap is the doping nd, and at the depletion region you are going to have this as 0, and similarly on this other side, okay, similarly on the other side you are going to have this, and Na is much larger than Nd, so let me get rid of this. So is going to do this, so Na is much larger than Nd, and this is going to be equal to Pp, which is approximately equal to Ni square over Na, and this is sorry, mistake, I did two mistakes here, beg your pardon. Okay, so let's do this again. So Nn is approximately equal to Nd, and this Pn is approximately equal to Ni square over Nd. Here this Np is going to be equal to Ni square over Na, and this is approximately Na, so this is going to be Pp, and this is going to be Np. Okay, so now this makes sense. So this is called depletion region because it is devoid of, what is it devoid of? It's devoid of minority carriers. It's not devoid of majority carriers. Majority carriers are still Nd. Majority carriers here are still Na. So this depletion region is not devoid of carriers. It is wrongly taught in the class. Depletion region is devoid of minority carriers. They become 0, while the majority carriers are still there to operate. Okay, so this is the carrier distribution. So I have seen p-n junction, I've shown you p-n junction in terms of all these. Okay, so I'm going to stop here for this session where we have seen p-n junction. Later on I'll describe where this p-n junction is used, right? It is used in number of places, so we will see examples. So for now I am going to stop.